Yeah, I do think we can get started.
Okay.
Thanks.
So, good afternoon, everyone. My name is Martin Min from NEC Labs America. So today we'll talk about the second lecture of deep learning. So in this lecture, I plan to cover deep supervised learning, especially about the feed-forward neural networks, convolutional neural network, and recurrent neural networks. So in supervised deep learning, basically given the network an input, for example, an image with three channels, the red, green, and the blue RGB channels, and then we want to predict the category of this image. For example, in the ImageNet challenge, given each image with the size of 224 by 224, we want to classify this image into 1,000 categories. So this is you give the input and the output, and then you train the neural network to backpropagate the signals of the error signals to train all these kind of parameters. This is the supervised deep learning. So in traditional supervised machine learning, for example, when you fine tune, you need to tune a hyperparameter of your model called such as SVM. You often use five-fold cross-validation, right? And then you split your training data into five folds, and then you just like use each fold as a validation set to fine tune to choose the best hyperparameter that works well. For example, the hyperparameter C. And then after you set the hyperparameter, and then you test it on the test data. But in deep learning, we usually don't do that, and we usually have a large like a validation set, and then we just like tune the hyperparameters on this validation set, and then you just like test your test your final deep neural network with the chosen hyperparameter on the test set. But of course, if your data set is reasonably large but not very large, you can still do five-fold cross validation, but people don't do that. So we talk about the supervised deep learning. We have the input features, for example, the RGB pixels of the image, and then we use a deep neural network to learn the features, and then we define the architecture of the neural network, and then we need to define a good error function, loss function. For example, the mean squared error, hinge loss, cross entropy loss. And then we use some kind of optimization algorithm, such as the stochastic gradient descent with the momentum or like an atom to train our neural network. And then we get a very good performance on the training data. We test it on the test data. As we talked about, we just tune a hyperparameter on the validation set. So for the one specific architecture of the deep neural network is called the fully connect layer. So in fully connect layer, so all, for example, in the units for all the units in this layer will be connected to all the other units in the above layer. So you see, everyone is connected to everyone. If you write it in the matrix multiplication, y is just equals w this is a matrix with the dimensionality of this feature hidden activity hidden layer, and the dimensionality of this layer. If this is p and a q, so the w is just p to q. Okay, it's a fully connect layer in the matrix matrix multiplication form. For activation functions, we after you apply this kind of like a fully connect layer or some convolution layer we'll talk about later, we need to have we add the non-linearity to this kind of output hidden units. For example, you can have the sigmoid function, and then you can have the tanh function and the ReLU function. For sigmoid function just takes this form. For ReLU, it's just like a max 0 and x. So basically, you add the activation function element wisely on each output unit. So for example, for its ReLU function, if the output of this output unit is negative, you just output 0. If it is positive, you just activate, just output that value, just x. So x is the input to this output unit. So there are other types of activation functions, for example, leaky, relu, max out, and elu. I will not discuss it. For the sigmoid activation function, the y equals 1 over 1 plus exponential raised to power of negative z. Z is the input, this output unit, this sigmoid unit. And for the tanh, it takes this form. And this is the shape of the sigmoid unit with the input z here and the output y here. Y should put here. This is y, and this is z. And then for the tanh function, the x-axis is the z, and then the y-axis is the output. It takes this form. And then the gradient of this sigmoid unit, that's the partial derivative of dy respect to the dz, and then it will have this form. And then for the tanh function, it will have this form. You can see that the gradient, if we write the gradient dy with respect to dz in terms of y, it will be y times 1 minus y. And for the tanh function, the gradient of dy with respect to dz is, you write it in terms of y, it will be 1 minus y squared. Basically, this y is just here, and this y for the sigma function is this form. So I just write this gradient in terms of this, output unit. You can see that for both the sigmoid activation function and the tanh activation function, the gradient is always between 0 and 1, right? You see, it's always between 0 and 1. That's why, when you have multi-layers of these kind of fully connect layers, and then each hidden layer has this kind of like a tanh output activation function or sigmoid activation function, you multiply this kind of 0 and 1 number many times, the gradient will vanish. That number, the gradient will be smaller and smaller. And then the deeper the network, the smaller the gradient, and then it approaches to 0 very fast. So that's a gradient vanishing problem. But when you look at the ReLU activation function, and this is a shape of the ReLU activation function. And then, of course, we talk about if it is like a negative, you just output 0. And then if it's like a positive, it just outputs that input x or z. You can see that, the gradient is always 1 or no gradient, right? So the gradient, you multiply the gradient 1 many times, it's still 1. So your gradient will never vanish. That's why, the ReLU activation function enables us to train a very deep neural network, because we don't have the gradient vanishing problem. But it has some other problems. For example, they cause the dead neuron, or the activity of the output unit is not bounded. And then we will not talk about it later. And then people come up with some other ideas to fix these issues. So another type of common used activation function is called the softmax activation function. Softmax activation function is often used on top of a fully connect layer, which transforms an activity vector z into probabilities of classifying the z into k classes. This is popular because we often need to do classification, right? For example, for the ImageNet, we want to classify the input image x into 1,000 classes, and then we need to use the softmax function with k equals 1,000, right? We need to classify the unit to predict like 1,000, the probability of 1,000 classes. So then you can use this kind of, the softmax activation function takes this form. And then if for image net classification, the j should be equals 1 to 1,000, ranges from 1 to 1,000. And then for each class, you have this logit value e, and then raised to the power of zi. Okay, and then the gradient of the softmax function with respect to the logit takes this form. Okay. Oh, okay. So to have a nice objective function, loss function on top of the softmax output unit, we often use cross entropy loss. The cross entropy loss will take this way. This is a target class. If the target class is either 1 or 0, and then this is the output of the softmax units. And then you can see that the loss function, the cross entropy loss function with respect to the logic input of the softmax units has a very nice form. It will be your like output of your softmax unit minus the target output. So why it is like this, and then you can do this kind of like a exercise after the class. And then you first need to calculate the partial derivative of the loss function of this cross entropy loss with respect to this this yj, because yj is the output of your softmax unit. And then you multiply this kind of like the derivative of your yj with respect to the zi is this form. You multiply them together, you can see that some terms will be canceled out, and then finally you will get this yi minus tj. So it has the cross entropy loss on top of the softmax output unit has a very nice property interpretation, because C will have a very big gradient when the target value is 1 and the output is almost 0. So, and also when the output value when the target value is 1, the output value of yj is 0.001 is much better than the output value of yg equals 0.000001, because the steepness of this kind of like here of this term will balances the flatness of this partial like a derivative. If suppose that we have a softmax output unit, but we use the mean squared error, that's very bad. The reason is that you will not have any steepest term to like balance this flatness term. So that's why when your target value is 1, your output real output when your desired target value is 1, but your output value is 0.001 or 0.001, there will be no difference. Okay, because you don't have that kind of log term here. Okay. So that's why the cross entropy loss is often combined with the softmax units for training your network. So when you use the mean squared error, you often use the linear output unit. You don't use the softmax unit or logistic output unit. Just try to think about why. Just as I talked about, we have a good property of this steepness, and then this partial derivative balance the flatness of the partial derivative, the output of softmax unit with respect to the logic input. So there are other kind of like common used loss functions, such as the hinge loss. The hinge loss is that the SYI is the output of your target class. The SJ is the output for the class that is not the target class. So this is takes the form as of the hinge loss. You can see the hinge loss is max 0 or S, the output score for the other classes other than your your target class minus your target class and then plus 1. So what does it mean? This score function tells us the score for the wrong class must be at least 1 margin smaller than the score for the ground truth class. Otherwise, there will be a loss incurred. Actually, it's very hard. When you first encounter this hinge loss, it's hard to understand. But actually, I can show you an easy way to understand it, because you see the loss is if this value is negative, right, and then you don't have any loss. But if this term is positive, we will have a loss. But you can see when this term is 0, when your output Sj for the other classes rather than the target class equals to Syi, means the target class score minus 1, it will be 0. What does it mean? Means that if the Sj is smaller than Syi minus 1, you don't have any loss, right? Because this will be negative. But if this Sj equals S1i minus like a 0.8, you will have a loss there. The loss is 0.2, right? So what does it mean? It means that you if Sj equals Syi minus like 100, that's very good because you have a margin of 100, right? So you see, just look at this, look at this, the Sj must be at least one margin smaller than Syi. So then you will not have any loss. The more negative this term, the better. What does it mean? It means that you assign a smaller value for the Sj for the other classes compared to the score assigned to the ground truth class. That's good. And then that's really what we want. So we want to make sure the difference between the scores assigned to the other classes and the ground truth classes must be at least 1. So it means the smaller this value, the larger this value, and then your neural network will be happy because there will be no loss. Okay. So this is how you can understand it easily. So the deep feedforward neural network is just a neural network with many fully connected layers and some nonlinearities. For example, this I showed an example of like a deep feedforward neural network with 2 visible units and then 1 output unit, and then with like 3 fully connected layers, and then with you can have a sigmoid activation function or relu activation function, applied to each output unit here. And then so following the computational graph we talked about in the last lecture. And then this is how we can do the backpropagation using a computational graph. The loss with the derivative of the loss with respect to himself, of course, is 1.0. The derivative of the loss, if we use the squared error, and then the derivative of the loss with respect to the output, target output y, this y here, will be like 2 times y minus the target, right? And then you can get the derivative of y, the output units, with respect to the w, and then with respect to the hidden unit, and then you just backpropagate this computational graph. Finally, you can get the gradient computed for every variables in this, for every variables, all the weights and the units, all these kind of weights, all the gradients will be computed by following this computational graph. You can do that, as an exercise, just looking at this lecture slide. So when we train a deep neural network, we often use stochastic gradient descent with momentum. So how we do it? So basically, we just split our training data into n mini batches with batch size b. We often use the batch size, for example, like 816 or like 32 or 128, 64 or such kind of like batch sizes. And then for the iteration or epoch ranges from 1 to a maximum number of iterations. And then for each iteration, we randomly choose a mini batch from this, with the batch size of b, for example, of 128, and then we calculate the gradient of your loss function on this batch of inputs, and then you just like when you use the momentum, you want to keep the previous gradient weight update. For example, you use the 0.9 times the previous like a weight update, and then you use some kind of small weight decay here because you want to penalize the larger weight in your deep neural network, and then you minus this is your learning rate. You minus the learning rate times your gradient, the gradient of your loss function with respect to the current weight, and then you just like this is your weight update for the current iteration. We call it VI plus 1. And then your current weight vector WI plus 1 will be your current weight WI plus this kind of weight update computed at this iteration. You keep in mind this weight update is related to the previous weight update in the previous iteration, right? And then just because we want to we don't want the the weight update to change radically here and there. We want to have the smooth direction of update this way. That's why we use that's why we use the use a weight decay here. This is a hyperparameter called weight decay. And then in the beginning, you often set this to be small, and then when your deep neural network almost converged, you set this with this momentum to be large. Okay, because when you reach the convergence, you almost reach your local optimal of your deep neural network. You don't want the gradient to change so much, right? And then you really want to change it smoothly. Finally, you can reach the local optimal of your loss function. So you can have two loops. The outer loop is over epochs. In a deep learning literature, we often call it epochs. And then in the inner loop, and then you loop over your mini batches. For example, for each epoch, and then you just say the batch size is say is 100, but your data set is 1,000, and then it means that 10 mini batches will almost cover your entire data set. So then you need to you will like for each epoch you run them the inner loop will loop like 10 times, right? Each time you choose a mini batch, and then you loop 10 times, and then that's one epoch. And then for the next epoch, you do it again. And then until that, your network converges. So, but the deep feed-forward neural networks works much worse than the shallow convolutional neural network, even on the minis. For example, for almost like a 8 to 10 layer deep neural feed-forward neural network without convolution, just like a fully connect layer and then ReLU activation function or or the logistic activation function, and then we got the error rate on the minis about like 1.0% error rate. But if we use a very shallow convolutional neural network, and then the error rate is close to like a 0.60%. So why? The convolutional neural network works much better than the deep feed-forward neural network without convolution. Here, let's watch a human and weasel experiment and explaining how the human like a convolutional human like a neural network works.
In this classic experiment by David Hubel and Torsten Wiesel, a microelectrode is implanted in the primary visual cortex, or V1, of an anesthetized cat to record the receptive field of a single neuron. A bar of light is shined on various locations in the cat's visual field. The microelectrode is connected to a speaker so that each action potential is registered as a clicking sound. The neuron fires vigorously to the onset of a bar of light at about 45 degrees. This firing pattern of the neuron is recorded by drawing X's along the bar's location. This is the on receptive field. In addition to the on receptive field, the neuron also responds to changes of light on the parallel space on either side of the X's. In this case, we hear clicking sounds when the light is turned off. These are the off fields of the neuron and are recorded as triangles. The neuron responds with more activity to the area below the X's, marked with 5 triangles, than the area above, marked with 3 triangles. Each individual neuron has its own preferred orientation and region of the visual field to which it responds. In this cell's receptive field, lines of triangles, referred to as the off-surround regions, flank the X's, which are the on-center region. The firing rate reaches a maximum only when the light is shined on the X's at the preferred orientation. Cells of the primary visual cortex with this type of receptive field and orientation preference are called simple cells. Widening the bar of light causes the firing rate to decrease. Diffuse light produces no response in the neuron, despite the fact that it shines upon the on-center region marked by the X's. Observe that the neuron fires when the edge of the light moves, leaving a portion of the triangles in darkness. Compare this again to the diffuse light. In this experiment, the same methods are employed to measure the receptive field of a different neuron in V1. Different orientations are tested until one is found that triggers maximum neuronal excitation, indicated by the intensity of the clicks. This time, a solid line is drawn to record the area of maximal firing. The cell measured in this experiment is called a complex cell. Compared to simple cells, a complex cell has a wider receptive field, and it fires when a bar of light is shined on any part of the receptive field. Like simple cells, complex cells are highly orientation selective. As indicated by the clicks, the further the orientation strays from the preferred angle, the less the cell exhibits an excitatory response. Complex cells respond to either light bars on a dark background or dark bars on a light background. Thus, complex cells can be considered more abstract line edge detectors than simple cells. They respond to the line edge on
Okay, let's go back to our lecture. You can see that in the Huber-Wiezel experiment, and then in the primals neuron, they can detect. It's kind of like an edge detector, and then for different neurons, and then they would detect different orientations and different arrangements of these kind of patterns, and then just like for image recognition. And then you have this kind of a simple neuron and this kind of simple neurons form into a hierarchy and into a complex neuron. And then all these kind of edge detectors, they prefer orientation, but they are but in the images, we have the image features, right? And then we have a lot of common features such as the different orientations of the edges, but these kind of different orientation of edges are not location specific. And then they say, for example, you want to detect a stroke in a handwritten a particular orientation of a stroke in a handwritten digit, right? This kind of stroke can appear in any place of the input image. So to encode this kind of information into our network architecture and gets the inspiration from this Huber-Wiezel experiment, people discovered convolutional neural network. So the message from the last lecture is that the deep learners should combine their knowledge with large-scale data to grow programs, and then encode the essential knowledge into the network architectures, and let the backpropagation and stochastic gradient descent do the heavy lifting. So how can we encode this kind of the space or the location invariant detectors, or edge detectors, or what kind of Gabor filter detectors into our image classifier? And then So one way to do that is use convolution. So in a convolution, in 1998, Yan LeCun invented the convolutional neural network. For example, if he wants to recognize this letter A, and then he has the convolutional layer, and then it's just like an image. It's a edge detector. You can think about it's a detector, and then as the very similar, analogous to the detector used in the Hubble Weasel experiment. It's just a linear patch with a learnable parameters, and then they just like do some kind of like a scanning on all these kind of like locations until they get a fire, and then that's the they record they just like calculates the output of this detector everywhere, and then they get the convolutional they have a convolutional layer, and then that layer, the output of that layer will be the output of this convolutional layer. They replace the fully connected layer with this kind of like local convolution, means that's the local matrix vector multiplication or element-wise like multiplication, and then just like repeat this filter in different positions of this image. And then they can have like just because similar to the Hubble Weasel experiment, in the primal vision visual system, we have many different kinds of like types of edge detector. So then to simulate that, we can have many different kinds of like convolutional kernels. So each kernel will produce output that is this big. So if we have like 100 kernels, we will produce like 100 output planes. And then after the convolution, and then we apply the nonlinear activation function, either it's a tanh or sigmoid or a ReLU, and then this is the final output of non-linearly transform the convolutional layer. And then in the next layer, we can do this. We can design another like higher level edge detectors based on the convolution, and then we will have another types of convolutional layer, and then get the output reach the higher level representation of this image. And then we can do this kind of like repeat this convolutional layer operation again and again. Finally, we have some kind of fully connected layers, and then we get the output with the softmax output unit to do the image classification. So this is the overall architecture of this convolutional neural network. Let's go to the details and how this convolution is actually performed. So first, let me give you an example of 1D convolution instead of showing this kind of images. Let's say the image is a one-dimensional image, right? The one-dimensional image has the length of 5, and then our like convolution will be, we have a 1 times 3 convolution. It's a one-dimensional, and then we the input size of the image is 5, and we do the padding on both sides, and then the length of the 1D kernel is 3, and then strat is 2. Strat means that because as I talked about, we need to slice that kind of convolutional kernel across different positions of the locations of the image to identify some patterns that match this edge detector, right? It's a 1 0 1 1 0 minus 1. You can think about each kernel is a template. If input matches this template, and then we will get a maximal very big output. If some kind of inputs, a portion of the inputs, completely different from this kernel template, and then they will have a smaller input, right? So then you can see that we just slide this 1 0 and minus 1 across this across the input. We have the element-wise multiplication, and then for the first position 0 1 and 2, element-wise like multiply the 1 0 minus 1, we get the output of minus 2. So we just move this sliding window here, and with the and then if we move one step, the stride is called 1. But actually, we move 2 steps. We start from this position, right? And then if we move 1 step, we should convolve this one with this guy. But actually, we use a stride 2, so actually we convolve the 2 minus 1. 2 minus 1 and 1 with this 1, 0, and minus 1. So 1 times 2 plus minus 1 times 0 plus 1 times the minus 1, we get this 1 here. So then, we just convolve this, move this, 1D convolutional kernel, and then just move to the next position with the stride 2, because the last position is here. When you use the stride 2, you should start from here. So next time we just convolve a 1 minus 3, 0 with this 1D convolutional kernel. And then we should notice that for each convolutional kernel, we also have a bias term, but here the bias term is 0. So I just for sure to demonstrate, to illustrate the example, and I didn't put any bias term here. So this kind of convolution layer is 1D convolution is actually very powerful. We can use it for sentence classification. For example, we can classify this sentence, wait for the video and don't run it, right? We want to know, is this a positive sentiment? It's a recommendation or not recommendation? So then we need to output 1 or 0 for this sentence, right? So what we do is that we can have an embedding for each word here, wait for the video and do for all these kind of like a word. And then we use the 1D convolutional kernel, and then just like it's the same thing as here, but difference is that now the convolutional kernel is like the dimensionality is not like a 1 by 3. So if your convolutional kernel size is 3, but your embedding vector is 10, so then each convolutional kernel is actually 3 times 10 instead of 3 times 1. So the idea is the same, right? You move that kind of like a 3 times 1, 2, 3, 4, 5, 6, 7. We'll have I showed like a 7 dimensional embedding here. So then it is just like if your convolutional kernel size is 2, then it is just a 2 times 10 vector, and then you just like a 2 times 10 matrix convolved with the 2 times 10 embedding of the sentence, and then you get the output of your convolutional kernel, and then you apply the nonlinear activation here. And then this is how you do it for sentence classification. Now let's show how we do this for 2D convolution. The 2D convolution is the same as the 1D convolution, except that our convolutional kernel is not a one-dimensional. Actually, it's a two-dimensional. For example, you just move it like it's a matrix instead of like a 1 by 3. It's a 3 by 3, right? It's a matrix. So let's see how it is done in some in some cartoon picture here. You can see the animation here, the convolution. You have the 3 by 3, and then you just move it. The stride is actually 1, so you move it like a step by step. And here, so this is some padding here. They have more padding, different paddings, and then because sometimes you want to convert a smaller input into a larger output, so you can add paddings to your input and then you apply the convolution. Okay, this is a cartoon picture of how they done in the. Let's go back to our presentation. Yeah. So let's look at it how it is done in the in actual RGB images for image classification, because each image has the 3 channels, right? RGB channels, and then your kernel will be like this. For example, here this kernel is 3. Say it is 3 by 3. This is 3. This is 3, and the RGB is like a 3 channels, right? You see, this is your actual kernel look like this. It's a 3 by 3 times 3 cube. Why? Because you have a RGB, right? You have RGB channels, and then you need, because each kernel, each position here needs to have 3 numbers, RGB numbers, to cover that. So what you do here, you just use the element-wise convolution. This is your input image, right? Your image here might be, say, it is 128 times 128. This is your image size, but you have 3 channels and then RGB channels, and then each position is a number. And then you convolve that kind of RGB image with your kernel. You just move your kernel like a, move this kernel in your image this way, right? I can see that the sliding window is actually 1. You can see, move step by step. And then when you convolve it, and then you get an output here. Each time you convolve it with this kernel, you get an output here. Why it becomes, one number? The reason is that you see, you just like you convolve, you linearly, element-wisely multiply your image input with this kernel. You need to sum them, right? Although you have 3 RGB channels, but you sum them because each RGB, this is channel is a value, right? It's a 3 number. Finally, you need to sum out these 3 numbers, and you get this. Okay. You think about this is like say this is a 3 by 3 kernel. How about you have a 1 by 1 kernel? What does it mean? So you can see that if you have a 1 by 1 kernel, what does it mean is that you just multiply the original, for each kernel, you just multiply the original image by a scalar number, right? This is a 1 by 1 kernel. But the thing is that how about if you have many different like 1 by 1 kernel, and then you see that it turns out the 1 by 1 kernel will serve as a fully connect layer. Okay, you can think about like let's go back, let's go to the slide to show how this kind of done in numbers. You see here. So this is your RGB image, right? This is the R channel, G channel, and then B channel here. And then your kernel size is actually 3 by 3, but you should notice that now you have like how many kernels here? You have 2 kernels here. But please note that even if you have 2 kernels, each kernel has the RGB channels. That's why each kernel has 3 matrix. You 3 matrix, and you can see that. Let's stop and then see. Yeah, just stop it here. You can see that for the second kernel, right? And then you element multiply them, and then you multiply this kernel here to this one, element multiply them to this part of the input, and then for this the G channel, you do the same thing. B, you do the same thing. But then you need to, after you get the 3 numbers, you need to sum of them. Sum the values. You get 3 values for each R channel, B channel, R channel, G channel, B channel. For each channel, you get a number, and then you need to sum it, and then you plus the bias term for this one is 0, and then you get the output of this, corresponding to this position of the input. This input, this position of the output corresponding to the input computed from this, for this 3 by 3 region of your original like RGB input. This is how you do it, like in reality. So any questions so far? So I think sometimes people are confused about the convolution. They don't know how it done. Actually, it's very simple. It's just like convolve this, move your kernels, move your kernels and then cross different positions. But please note that because your input has 3 channels, your kernel is not 1 channel. It's not 1 matrix. You have 3 matrices there, and then you sum of them.
So I have a quick question.
Yep.
Clearly it works well for images because it's like a 2D/3D spatial images, and you can like convolve it over like the spatial map. But are there other types of data that are non-image data that you can like do this convolution with for the convolutional neural network?
That's a very good question. So you are asking that, whether, so when you do convolution, for images, what you mean is that you really identify some kind of like a template pattern that is space invariant, right? So either in images, you can think about it in an image. I want to identify like a human eye, right? So this human eye can occur like anywhere in the image, right? Because human has two eyes, and the human's face can occur anywhere in the input image. So that's why I need to use the convolution. Like the convolution actually just exactly looks like the human eye with the in the pixel value if you visualize it. And then I just like a scanning this human eye kernel across all different positions of this image. That's why I can identify human eye. For sentences, I want to identify a specific like a pattern of word. For example, I want to identify the word happy. And then because your kernel is the embedding of happy, and then you just like a scan your like a happy kernel across all different positions of sentences. That's why you can identify the happy word, right? But if your input does not allow this kind of like a spatial invariance, doesn't have this property, it's not good to apply the convolution, right? So you really need to think about what kind of property you want. You can apply the convolution only if you know that you want to identify some kind of like a space or location invariant patterns. Does it answer your question?
Yeah, thank you. And I was also wondering, like, obviously you get like edge features when you do the convolution on images, but for words, what would that look like?
Look like the can you see my screen? Let's see. You see it here. Are you seeing? I'm sorry. Are you seeing my screen now?
Yeah.
You see, like this is a sentence, right? Wait for the video and don't run it. Actually, this is a sentiment analysis, like a sentiment, because I want to know whether this comment is positive or negative. So actually, you see like a don't rent it. This is definitely negative. But then your convolutional kernel will encode some kind of patterns of positive and negative. It matches this, because you need to scan this kernel across all these kind of different positions. If it matches this don't rent, and then it will know that this is negative. But the good thing about the convolutional deep neural network is that you don't need to handcraft this kind of like a don't rent like a kernel, right? Because you provided the deep neural convolutional neural network with a lot of matched pairs of this actually is negative and this is positive, and you do the back propagation, it will automatically learn the kernels and then matches. Oh, this filter will actually account for the don't rent the pattern. This will account for the unhappy pattern, and then that kind of like will account for the excellent pattern, and the other will account for the say the great pattern, something like this. You understand what I mean?
Yeah, that makes a lot of sense. Thank you.
Okay, thanks. Yeah. Okay, let's go ahead and into the next. So in 3D convolution, it's the it's the same. It's very similar to the 2D convolution, but actually you have another dimension of freedom to move your of your kernel, because you see in a 2D kernel, compared to the 2D kernel, right? Even if you have the RGB channel, but you never move in the RGB direction, right? Because your kernel has the RGB, has the 3 like channels. But in 3D like a convolution, for example, video, you have another, instead of have the spatial of the length and the width of the 2D dimension, you also have the freedom dimension of another freedom dimension of time. So you can move your convolutional kernel across the time domain, and then so you can do the video classification, right? So that's this is cartoon picture shows the 3D convolution. It's the same as you saw the examples of 1D convolution, 2D convolution, and 3D convolution. It's actually the same thing. So, but the thing is that the convolution cannot identify some kind of like a spatial invariant pattern. For example, because when you run the convolution, right, you will get the output almost the same size of your input. But how can we get the shrink this output size? We can do the pooling. So it's like for example the max pooling, and then if my pooling kernel is pooling kernel of pooling kernel size is 2 by 2. Actually, if I do maximal pooling, I will just take the maximal in this in this 2 by 2 grid, and then this will be output like a 6. This will be output 8, and then we also have a strat there. Here the strat is 2, because if the strat is 1, the 2 by 2 the first 2 by 2 pooling is here. The second should be here. But if you use a strat 2, you start from here, you skip this one, and then you move here. So this is how you use the strat and the pooling size to control, what kind of resolution, what kind of like output size you get. For example, this is your 4 by 4 input, right? If you have a 2 by 2 kernel, and with the strat 2, you will reduce this input of 4 by 4 into a 2 by 2, right? But say if I have a 4 by 4 like output, 4 by 4 like pooling kernel size, and then it means that means that if I have a and then I will, for this one 4 by 4, I will only take the maximum of this 4 by 4 like a matrix, and then you see. And then if I use a strat of 1, maybe you only get like a 1 times 2 output. You got it. So you just use the max pooling and the strat to control what kind of information you want to extract from your large input. Because your original input is like this. All these kind of information are like are redundant, repeated with each other. We really want to know is that if there is an edge in this pattern, right? If my max pooling kernel is this big, I will say, oh, there's an edge here, so I will output 1. So I don't need to replicate all the detailed information. So the pooling is actually used for feature abstraction. You can abstract from the lower level features to the higher level feature, right? And then if you want to know whether a person existing in this image, when you use the pooling layer, and then you can easily arrange to a high level like a feature plane to say, oh, this actually, this pixel in a high level feature plane corresponding to a larger input in this input. Actually, this person is actually here. That's why we use the pooling strategy to abstract the feature from low level details to the high level concepts. Okay. So another common trick used in the deep convolutional neural network is called like data augmentation. For example, you have the input image cat. You can do the blackout cutout of this image. You get another image. We can still see this is a cat. So you from this input image, or you can use a flipping, right? And then you use a clipping, and then we can create different copies of this image, and then we still assign all these kind of like augmented images like with the label cat. So then you can use the augmented images to train your deep neural network. Then you have more data. For example, you only have 1,000 data points. Using this kind of like image data augmentation, you can probably create like a 1 million data set, like 1 million data points with with different like augmentations of the input image. So you can think about how to use this kind of trick for your bioinformatics or biomedical data, like augmentation. So another popular data augmentation trick is called the mix-up. For example, you have a butterfly image, right? This is a butterfly, and this is like a helicopter. And then instead of just do some clipping or like a flipping, and then you can do the mix-up. I multiply this image by I convex combine these two images, and then I use a different like a probability, different weight assigned to this to each image. For example, assign a bigger weight to the helicopter and a smaller weight to the butterfly, and then I linearly combine them, convexly combine them, and then you will get to this image. I will assign this, the new image with the label of 0.11 butterfly and 0.89 helicopter. And this is a using this kind of trick, you can, from these two images, you can create a lot of like a convex combined like images with the soft labels, right? So this is another efficient data augmentation trick. So let's see some kind of like a real case study with the AlexNet, how they did the ImageNet classification. This is the actual like AlexNet structure. So this is the original image is the input image is 224 by 224, and the channel is RGB3. So the actual input is a cube of 224 times 224 times 3. But when the first first they use the convolutions of like 5 times 5, and then they use a 3 times 3, and then use a nonlinear use a ReLU activation, and then they do many different like repeat this kind of convolution with different size of convolution layers, 5 by 5, 3 by 3, 3 by 3, and then fully connect layers. And then they just like a softmax output, and then they backpropagated all these signals to train this deep convolution neural network. You can see the AlexNet has so simple architecture, but it revolutionized the image classification task. So and then they use the stochastic gradient descent with the momentum as discussed before to train this AlexNet. And then Alex found out, when he used the ReLU activation instead of the softmax activation, it converges much faster. Okay. So there are some other like different architectures invented in the literature. For example, the VGGNet or ResNet, and then here show some examples. I will not go to the details. And then how to calculate the parameters, it's easy. You just calculate, how many kernels you use and how many parameters in each kernel. For example, for the 1D convolution kernel, we show that if you only use like one kernel, your parameter is only 1 times 3, only 3 parameter. And then if you use 100, that's a 1 times 3 kernel, your parameter will be 1 times 3 times 100. Simple. And then just do this kind of calculation, and then add the parameters of your convolutional kernels. So a natural question is that if we make our network, the deep neural network, the deeper, do we get a better performance? People find out it's not the case. And then if you train, for example, on the ImageNet classification, they just use the VGGNet. If you use a 20 layer, and then they get the training error of this low. But if we use the 56 layers of convolution, the training error is even higher. And then people wonder why this can happen. They find out, the problem is that, the information cannot be efficiently propagated to the upper layer. So then they invented a new, like a new trick called an identity mapping. Because identity mapping means that for the upper layers, you have the skip connections. So instead of like for this like input of this layer to this upper layer, instead of just go through the many convolutions and ReLU activation, and then how about just like add the original input to the original to the output of that upper layer. So then it means that if my original if the features learned at this hidden layer is actually very good, then we don't make this convolution small network learn much. We just set it to 0. So if these features learned at this layer are not good enough, and then we will learn more. So then they will have the skip connection here. They have an identity mapping from the lower layer to the top of the upper layer, and then it will this kind of phenomena will not happen anymore. So they can always get a better performance. So there are different architectures of residue layers, but the idea is the same. We just want to have the skip connection, and then to make sure that we have identity mapping. The good features learned in the lower layers are preserved in the upper layers. They will not be discarded. But if you don't have this kind of identity mapping and a skip connection, and then you always want this network to learn something, sometimes this the features learned in these upper layers will ruin your good features learned in the lower layer. But with the identity mapping and the skip connection, that kind of phenomena, that kind of thing will never happen. So this is a detailed architecture of the ResNet. compared to the VGGNet. They have the skip connections, many skip connections here, and then just architecture engineer and nothing else. And then they figure out for the ANC Labs American model, and that's the champion model, with the error rate of 30%, close to 30%, but with the ResNet, we can reduce it to 3.6%. That's a great achievement and a revolutionary success compared to the original, even compared to the original Alex model with the 16%. That's great. So let's I will just skip this because it's I want you to learn the PyTorch 60-minute blades of PyTorch tutorial by yourself. It's just easy, and then start with the basic tensor, and then the autograd, and then train a simple convolutional neural network as in the Yan Kang's paper. And then I want to highlight is that instead of learning this kind of tutorial, you can still parameterize your own forward and backward function using PyTorch. So I suggest you look at these examples and then try to implement your experiment with your own neural network by yourself, and try to write your own forward and backward by yourself. Okay, you just need to write your own forward, and then you can either use the autograd and then to write your forward, and then the backward is automatically done by the autograd, or you can use you can write your own backward, and then using this kind of interface. So what can we do with a pre-trained deep neural network? For example, we pre-train a deep neural network on some kind of a gene classification, or on some kind of image classification. What can we do for that? What can we do use this kind of pre-trained net? We can actually use, we can perform simple transfer learning. For example, for some tasks, we have a lot of examples, training examples, but for some other tasks, we don't have many examples. What can we do? We can just using this kind of pre-trained net with a large number of training data to get the features for the tasks. We don't have many, we don't have many training data, and then we use the extract the features from the pre-trained net as the new feature of our new task. Of course, we need to assume that the new task should be highly related to the task that has a lot of training data. We can also perform few-shot learning. For few-shot learning is that for a task we don't have many training examples, we can use the features on top of the pre-trained net as a prototypes, and then we just perform simple k-nearest neighbor. And then for few-shot learning, we can even perform zero-shot learning. Zero-shot learning is that for example, we for a task, we don't have any training example, but we know that the task is semantically related to the classes of the original task. I have a lot of training example. For example, when you have a deep neural network pre-trained on the ImageNet with 1.2 million training examples, but I want to know whether this image is a zebra. But in my new task, I don't have any training example for zebra. But I know that the zebra has the blue and the white straps, right? And then I just use to see with the red and with the black and white straps, and then I will find out which class descriptions in the ImageNet class has this kind of description of black and white straps, and then I can just use a convex combination of the original ImageNet classifier, and then to try to predict what kind of black strap exists, a white strap exists, and then in the current input image, and then to classify whether this is a zebra. So basically, I will show you an example here. For example, you have a test image of this. You never you never, see the example, but this example has some kind of descriptions of this guy, and then you just use the convex combinations of the class descriptions of this class, and then you can try to get the 1000 class probabilities of this image, and then use a convex combination of this kind of like 1000 class related to your target, like a description of your class, to predict whether this is the golden hamster or not. This is the zero shot learning. Anyway, this is some kind of like some kind of like extra like a material. You should know that we can use a pre-trained ImageNet or pre-trained classifier on a larger amount of data to do a lot of things, including the zero-shot learning or few-shot learning, or like or some other like transfer learning. So a natural question is that what kind of like filters do we learn using the backpropagation? Does it correspond to the Hubel-Wiesel experiment? You can see that actually, surprisingly, it does. You can see that the lower level convolutional filters, they do like automatically recover some kind of like edges, and then the upper like layer convolutional filters, they do correspond to some kind of object shapes, right? And then so that's why we can see that the convolutional kernel, the convolutional neural network is actually biologically plausible, and it's a simulation of a human visual system. So I will skip this to the about the recurrent neural network. Let's just go directly to the recurrent neural network. So okay, how can we transform a standard neural network to the recurrent neural network? So the recurrent neural network, in a standard neural network, you have the input X, and then you have like you have the many hidden layer representations, and then you get the output Y, right? How about like we have the skip connection to connect the input into every layer? So suppose that this is our input, is not a simple image, it's a sequence, right? Then we just use this input, different parts of the input to connect to this different, like we just like transpose the architecture of this feed-forward neural network. It will be this way, right? Actually, this is the architecture of a recurrent neural network. So you see, the recurrent neural network starts from a hidden representation. It's randomly initialized H0, and then for each hidden layer, we just like input different like a part of the input sequence, and then we get the output. So this is a recurrent neural network. You can see recurrent neural network is nothing different from a feed-forward neural network we had about with the skip connection. It's the same thing, but in each time, instead of like each time step, instead of feeding the whole input, we just input the part of it. Okay, so this is the recurrent neural network. So when you write it down, so in our like original like feed-forward neural network, HT plus 1, HT is only a function of HT minus 1. But here in the recurrent neural network, the hidden representation at the T step is not only the hidden representation is not only the function of the input of the previous hidden representation, but also the input, part of the input. So that's a recurrent neural network. Okay, so this is how you like write down a vanilla like a recurrent neural network with some tanh functions. So in the recurrent neural network, we can have one-to-one, means that one sequence input to the one input and one output. We can have one output, one input. We have many outputs, or we have many. So many to many is very popular in the recurrent neural network, or many to one. So basically, this is your sentence representation. Sentence, this is word 1, word 2, word 3 in your sentence, and then you have a hidden representation, and then you get the output, the sentiment of this sentence, the sentiment category of your sentence. Or you can have many, like many to many output for each like a word of the sentence. I want to classify what's the sentiment class of that word. So these two architectures these three architectures are most popular in recurrent neural network. So keep in mind the recurrent neural network is almost the same as a straightforward feed-forward neural network. Okay, many-to-many recurrent neural network. And then I will skip this, and then you can in the vanilla recurrent neural network, you can use the backpropagation through time. But what it means that if your sequence is very long, you don't try to get the output of your after compute over all these kind of inputs, and then you backpropagate. We just chop these long inputs into many different segments, and then we update the recurrent neural network, just it's the same thing as updating the feed-forward neural network on the segments of this input. Okay. So I will show you some examples. This is corpus is like a character RNN. You can try that. The code is like open source here, and then basically it's just like a recurrent neural network trained on some text. You can predict the next word given the previous words in this sentence. And then after you train this recurrent neural network, you can run it, start from the random initialization, or start from several words. You can write an article. And then I think some people will, the next lecture will cover details about the NLP. I will not talk about in details. So, but the problem is that the vanilla recurrent neural network, they have the vanishing gradient problem. It's the same as we encounter for the feed-forward neural network. The idea is the same. So then people find out we can use a skip connection layer exactly as we talk about in the residue net, and then to fix this kind of the vanishing gradient problem. Okay, so then if you have a sentence, instead of have one direction like a recurrent neural network, you can also have a second direction, have the backward direction. And so, for example, you want to classify the peptide of a protein segment, and then you just you can have one direction recurrent neural network trained this way, and then another direction of a recurrent neural network trained the other way. And then you can use this kind of thing for for sentence classification or machine translation. Okay, I will not go to the details, but the training you can just use the package, call the package LSTM or GRU implement in the PyTorch to do it. You should have the high level understanding of it. So it's the same thing as training recurrent neural network, as a feed-forward neural network. So in summary, so we talk about the activation functions, loss functions, the training the convolutional neural networks, backpropagation, and mini batch stochastic gradient descent. And then we focus on talking about the convolution, operation, pooling, and we just give some examples of AlexNet, VGG, and ResNet. And then we briefly talk about the applications of CNNs and the recurrent neural networks. Okay, thank you. So next lecture, we will talk about the deep generative models. So any questions? So the recurrent neural network is, I just briefly talked about because it's very similar to training the ResNet or training the feed-forward neural network. So the only difference is that instead of training the layer by layer, and then we call it time step. But in the feed-forward neural network, we call it layer 1, layer 2, layer 3. But in in the recurrent neural network, we call it time step 1, time step 2, time step 3, and then but it's the same. Any questions so far? Thank you.
I have a general kind of question related to network architecture and stuff. So you talked a lot about BGG and ResNet, which are really famous, designed by to be really famous, and they obviously went through a lot of testing to arrive at these architectures. And maybe they're aimed at CNN to do image classification or such. But say you have a problem that is similar, but a little bit different from what they apply it on or what they're doing. So you might want to base your architecture off of ResNet or VGG or something like that. But let's say you don't have the resources to, really go into a lot of detail and to tune all the parameters, because obviously there's so many different combinations of layers and parameters that you can tune. How would you say, or what would you recommend to like tuning these, or do you think just directly using their architecture, obviously maybe changing the input layers a little bit, but just how do you think about this problem of tuning really complex models that you don't necessarily have the resources to try every single parameter?
That's a very good question. So I think practically, most of the time you don't have enough resources to tune this kind of like a very deep neural network. For example, this kind of like 100 layers of ResNet, right? So, but you need to know the what are the most important things. I would say the most for a lot of problems, either if it is for segmentation, right? If you want to do image, you need to think about the types of problem you're facing, right? If it is image segmentation, you probably want to check the architecture of the UNet, right? If it is the fully convolutional neural network. If it is your task is only for classification, the first thing coming to your mind probably just say whether this is there any kind of like a spatial invariance in my input, then I need to use the convolution, right? And then then you think about whether I have enough data. Do I need to think about I should use the ResNet? So then this is the first type of thing you should think about: convolution, or use ResNet, or you use the fully connected, just like a simple like a deep neural feed-forward neural network with fully connected layers without any convolution, right? This is the first type of thing you think about. Second thing is that you need to think about how much data do I have, and then you need to compare. You need to compare the information content in your data to the number of parameters you want in your network, right? You don't want to replicate this kind of like a VGG or something, because you see they have so many different like hyperplanes. 512. What does it mean? It means that they have 512 3x3 kernels. If your problem is very small, you probably don't need to replicate this architecture, right? Even if you want to replicate this VGG, you want to say, they say I start from maybe like 10 kernels will be enough for my problem, because the information contained in my data is only say like say 20,000 bits, right? 20,000 bits, and then of course you need to compare the 20,000 bits with the information contained in your model parameters. You want to make sure these kind of two parameters are comparable, right? And then, or if there's even if the over parameterization network often over parameterize the deep neural network often work very well, but still you don't want to have a huge network in your application on a very small amount of data, right? That's why you need to tune the number of kernels you use. So I think that's and another thing you need to think about because after you fix your architectures, you really need to worry about the performance. So I think two things are very important. One is the learning rate. The other is the batch size. So I think there are not much to be afraid of. When you first think about it, you think, oh wow, there are so many different hyperparameters to tune. But actually, when you do it in practice, not many, just maybe the learning rate, and then the batch size, and then probably how many hyperplanes kernels I want to use, and then how many layers I want to use, and then that's it. And then if you choose to use the deep convolution neural network. So not many. For a fully connected layer, it's even simpler. And then just think about, okay, and then how many hidden units do I want to use for each fully connected layer? And then how many layers do I want? And that's it. Does that answer my question?
Yeah, thank you.
Okay, thanks. Yeah. So any other questions? But pay attention that, for even if you want to use, for example, the pre-trained net on BERT, for example, model, don't copy exactly BERT model, whatever, because the BERT model, they probably use a lot of hyperplanes, right? Convolutional, a lot of like attention heads or something. It's the same thing as the convolutional kernel. You don't need to use that many. You just reduce that number. Even if you want to have like, say, this user 50 layers, I would just say probably 10 layer will be enough for my application. They use 128. How about let's just try to say start with like say like 8 or like 16. Probably will be good enough for your application. Thanks. Yep. Okay, if no other question, I will stop sharing my slides. Thank you.